We will now look at message queues. Message queues provide a way of passing data between two unrelated processes, which means the two processes don't have to be associated as parent and child. They could be any two arbitrary processes. Moreover, the message queue can exist independent of the processes. A difference between message queues and other mechanisms like pipes and sockets is that message queues provide a message-based mechanism for inter-process communication. Unlike pipes and sockets, which provide a stream-based communication where bytes are flowing from one process and they are captured by the other process, and both processes have to be active at the same time in stream-based communication. Message queues don't work this way. Message queues, the unit of data movement is a message with a maximum size limit. The sending process, if it has a large amount of data to send, will have to split it into multiple messages and send out those messages for the destined process. The destined process would then retrieve those messages one by one. Now, an important thing to keep in mind is that in message-based communication, the sending process and the receiving process, they don't have to be active at the same time. In stream-based communication, they have to be. But in message-based communication, the message is sent out by the sending process and it is going to be retained in the message queue. After sending all messages, the sending process may terminate. At some point in future, the destined process or processes would then retrieve the messages from the message queue. When the unit of data movement is going to be individual messages, there is going to be a size limit imposed on each block of data, and Linux is going to define these two given constants, and they are going to decide the maximum size in bytes of an individual message and the maximum size of a queue. Message queues appeared along with shared memory. Therefore, you will notice that the naming is following a similar pattern. So we have message CTL, MSGCTL, which is similar to SHMCTL of shared memory. CTL stands for control, and we are going to look at the details later on. The next one is MSG get, message get, which is also similar to SHM get in that it can be used to form a new message queue, or it can be used to get a handle on an existing message queue. The code examples will illustrate the usage of this one. Now we look at message send. Message send is one of the two important functions which are used for sending data and receiving data from the message queue. So the first parameter, MSQID, is used to identify which message queue we want to send a message to. The second parameter, a white pointer, should be the address of a message. The third parameter is the size of the message. The fourth parameter can be used to control some options. For example, what should happen if the current message queue is full? And as described over here, one option is to specify this value IPC_no_wait. In this case, this function is going to return back immediately into the calling process without sending the message. Moreover, the return value of MSGSND message send would be -1, reflecting that message could not be sent. If you do not specify IPC_no_wait as the fourth parameter and the message queue is full, upon trying to send the message into the queue, it will cause the calling process to get suspended. The calling process will remain suspended until space becomes available in the message queue to deliver the message. On success, MSGSND message send returns 0. Next we have the message receive function, MSGRCV, and this one takes 5 parameters which I have split across 5 lines. The first parameter is used to specify which message queue to operate on. The second parameter should be a memory location where the retrieved message will be stored. So this should be address of a location which is large enough to hold a message. The third parameter is the size of the message that will be retrieved. The last parameter, MSG flag, can be used to specify additional options other than the default We now turn attention to the fourth parameter, MSG type, long integer. This one can be used to extract messages from the message queue in different ways. It can take a positive value, a negative value, or a value of 0. If you specify this parameter's value as 0, in that case, messages are retrieved from the message queue in the same order in which they were sent into the message queue by a different process. So the message queue behaves like a strict first in, first out system. The other possible values for the fourth parameter are a positive value, let's say 10, 20, or 30, or you could even specify a negative value, let's say minus 20, minus 30, and minus 40. If you specify a positive value, then only messages of that specific type are extracted from the message queue. This also means that a message queue has the capability to hold messages of different types, and you can selectively extract messages from a message queue. Now, if a negative value is specified as a fourth parameter of this function, then it can be used to extract messages of a type n or smaller. So let's say that if there is a message queue which has three kind of messages of type 10, messages of type 20, and messages of type 30. If we only want to extract messages of type 10 and 20, then the fourth parameter in this function should be minus 20. This will extract all messages of type 20 or below. Now let's turn our attention to the code example. And the very first thing that we have to understand is the format of the message. When we are going to use the message queues, we have the option to define our own message format. However, there is one thing that we must respect. The one thing that we must respect when defining our own message formats is to ensure that the type of the first field of the message is a long integer. As you can see in this box, this gives you the skeleton of how you can form your own message formats. You will use the struct to define a structure. The first field must be of long integer type. You can give it whatever name you like. And after that first field, you can define extra fields depending on your needs. So in this example code, we have a structure format shown my underscore msg underscore st. It is made up of two fields. The first one is a long integer and the second one is a character array. We will have two processes. One is going to send messages into the message queue, and the other process will retrieve messages from the message queue. So the first thing that we have to do is to form a message queue, and to do that, the usage is similar to shmget in shared memory. Over here we have message get, and you also have to specify a key value to uniquely identify the message queue. The return value of message get is inspected for errors, and then we have a while loop. In this while loop, you will see that messages are extracted from the message queue, and we keep on extracting messages by calling message receive. And this process keeps on happening as long as the contents of the message extracted do not contain the word end. So first you will see that there is message receive, which is called, and its return value is inspected inside this if expression. If the return value is -1, there was a problem in retrieving the message from the message queue, and this process will exit. Otherwise, this process will proceed and it will display the sum underscore text field of the sum underscore data. Sum underscore data is where a copy of the extracted message will be stored by message receive. The second if condition is the same convention which was adopted in our examples of shared memory. If the message contains the word end, then the flag running is set to 0 and this while loop will stop. Once this process comes out of this while loop, it is going to call messagectl to delete the message queue. And the way it is done is messagectl is passed on the command value ipc underscore rmid. Let's look at the other process. This process will deposit messages in the message queue. So we have the structure defined over here once again, and then we have call to message get. The return value is inspected for errors, and then we have the while loop. In this while loop, the first printf statement is going to prompt the user to enter some text. This text is captured using fgets and stored in the variable buffer. Then we are going to prepare our message. Sum underscore data is a variable of our above defined structure. The first field of this structure, the long integer, is assigned a value of 1. In the second field of the structure, we will copy the text that the user has just entered. After that, this prepared message will be deposited into the message queue using message send. And here you see the usage of message sent. The first parameter is the queue. The second parameter is the message that we have just prepared, sum underscore data. The next parameter is the size of the message, and the last parameter is set to 0. Message send is called inside this if expression, and if the return value is -1, something went wrong, and this process will simply exit. Otherwise, it is going to proceed and perform the next if statement, which will inspect if the user has entered the word end. Specifically, if the first 3 letters of the input from the user contain the word end. In that case, running is set to 0, and this process comes out of the while loop and simply exits. If you look at a sample output run, you will see that the sending process is started first, and the user is prompted to enter some text. Here I have entered 3 lines of text one at a time, and when I have typed end, the process exits and I get the prompt back. Notice that at this point only one process was started. Now I start the other process on the shell, and you see that it has retrieved all the messages which were sent earlier by the other process. Note that at this point the sending process has already terminated. This demonstrates a very important feature of message queues. The sending process and the destination process do not have to be active at the same time. This is a fundamental feature of message-based communication. Over here, you have seen it in action with message queues. This is also applicable to network communication, which is message-based. This is different from stream-based communication, where a flow of bytes is happening from one process to the other process. And for stream-based communication to work, both processes must be active at the same time.